Good morning, everyone. Today, I'm very glad to present my project, Privacy Preserving Top SNP Selection in Genome-Wide Association Studies. Next. My name is HaoranLi, a PhD student from Emory University. My project mentor is Xiaoqian Jiang, and joint work with Zhang Longji and Lucila Alhama-Trado. Next. The goal of my project is to design a privacy-preserving mechanism to select top M most relevant SNPs. Here, SNP is short for single nucleotide polymorphisms. We shorten genome-wide association studies as GWAS, improved from the basic Laplace mechanism. Here, we call our framework advanced Laplace mechanism. For the rest part of my presentation, first, I'll start with motivation and problem setting, then followed by the basic Laplace mechanism and our advanced Laplace mechanism. Finally, I'll discuss experimental results and some future directions. Next. GWAS have brought lots of benefits to the healthcare community. Not only can they provide useful information for diagnosis, patient stratification, and prognostic, but also help healthcare providers to customize the treatment to individual patients, which is most likely to be effective. Despite the benefits of GWAS, the public is becoming increasingly concerned about them because they may put patient-sensitive information at risk when used inappropriately. Lin estimated that 75 to 100 SNPs or fewer than 20 microsatellite markers can unambiguously identify a single individual. Most recently, DreamRank identified personal genomes by surname inference from the anonymized 1,000 genome data. Next. In response to these privacy disclosures, Euler proposed to release only the perturbed statistics which measure the relevance of a SNP associated with a disease, such as chi-square statistics, p-value, and so on, to replace directly releasing the original genome data. So the problem setting of our project is to release top M most significant SNPs under differential privacy, which is a formal privacy guarantee proposed by Cynthia's work. A randomized mechanism is differentially private if its outcome is not significantly affected by changing any individual record of an original dataset. Next. Assume we want to select top 5 most significant SNPs from 50 SNPs. The basic Laplace mechanism first computes the two chi-square statistics from the count of allele table for the ith SNP. Then adds Laplace noise with mean 0 and magnitude proportional to S over epsilon. Here, S is the sensitivity of chi-square statistic, and epsilon is a privacy budget that measures the level of differential privacy guarantee. The smaller the value of epsilon is, the stronger the privacy will be preserved. Using the perturbed chi-square statistics, we can rank all the SNPs and select top 5 SNPs with the first 5 largest noisy chi-square values. Next. Different from the basic Laplace mechanism, our advanced Laplace mechanism adds Laplace noise directly to the count of the allele table for the ith SNP. As shown in the figure, we first compute the noisy count from tilde-A to tilde-D by injecting Laplace noise with mean 0 and magnitude proportional to S prime over epsilon. Here, S prime is the sensitivity of the allele table, and the noise injected to all the 4 counts preserves epsilon differential privacy by parallel composition theorem. Using the noisy count, we can compute the final perturbed chi-square statistic value of the ith SNP, and finally rank all the 50 SNPs. We succeed in reducing the amount of Laplace noise injected to the noisy chi-square statistic value because S prime is much smaller than S. Next. Now I'll talk about our experiment results. In our experiment, we use 1 simulated data and 1 real data. The simulated data is generated by half sample and contains 8,531 SNPs. The real data contains 5,000 SNPs and is used for the iDASH competition workshop. Both datasets are publicly available on the website. We compare our methods with the basic Laplace mechanism, exponential mechanism with chi-square statistics as the utility function, and the GS-score method. The GS-score method is using GS-score as the utility function of the exponential mechanism, and the GS-score measures the robustness of a SNP changing from significance to insignificance. Next, we use the ratio between the size of the intersection computed from S0 and S and the size of S0 as the utility measure. Here, S0 is the set of top M SNPs ordered by their true chi-square statistic values, and S is the set of top M SNPs ordered by the perturbed chi-square values. The larger the value of the ratio is, the more accuracy of the algorithm will be. Next, in the HAP sample data, the original top chi-square values range from 0 to 75, with a large gap between the second one and the third one. Next, in these figures, the black line with square markers denote our advanced Laplace mechanism using genome type table, and the pink line with circle markers represent our method based on allele table. We can observe that both our advanced Laplace mechanisms perform better than other state-of-the-art techniques. There is a large gap between our methods and the basic Laplace mechanism and the exponential mechanism using chi-square, because smaller privacy budgets will lead to more noise on the original statistic values for basic Laplace mechanism, and smaller probabilities to select the top M SNP with larger chi-square for the exponential mechanism. The GS-score method remains around 0.8 utility values because it's an indirect way to measure the significance, and the rank due to GS-score may be a little different from the rank due to chi-square. Next, for the iDASH computation data, the true chi-square values of top 10 SNPs are much larger than that of HAP sample data, ranging from 100 to 800. So we use smaller privacy budgets for this data set. Next, we can see that our methods still perform better than other algorithms with epsilon ranging from 5 to 50. The utilities of basic Laplace mechanism and exponential mechanism are gradually increasing with larger privacy budgets. This is because the true values are much larger compared to the injected noise for the basic Laplace mechanism, and larger probabilities to select top M SNPs with larger chi-square values. GS-score has the same problem as in HAP sample data by keeping a constant utility value and not converging to one with larger privacy budgets. Next, to summarize, our project focuses on privacy-preserving selection of top M most relevant SNPs. The creative point is that we add Laplace noise directly to the counts of the contingency table to reduce the amount of noise added to the final chi-square statistics. From this project, I have learned how to select top M most relevant SNPs and their differential privacy, and how to adapt privacy-preserving frequent atoms mining techniques to apply in our context. Next, for future directions, we want to develop more advanced privacy-preserving algorithms to select top M most relevant SNP combinations. And we already have a paper submitted to 2014 Translational Biomedical Conference. Next, finally, I'll thank to my mentor, all the collaborators, all the professors, staff, all the other interns, the iDASH, DBMI, and NIH. So much for my presentation. I'm very glad to answer any questions you ask.